Hello everyone. Today we are in third part of memory organization of unit 6. I assume you all have watched previous two parts. If you have not watched, see that part first and then come to this part. In previous two parts we have discussed important topic like memory hierarchy, associative memory, that is also known as CAM, and the full form of that is content addressable memory. We have also seen what are different types of RAM, different types of backup memories, also known as auxiliary memory, and different parts of magnetic disk, magnetic tapes in detail. In first part, I completed the locality of reference. Just for the revision purpose, we'll again discuss the same. Analysis of large number of program has shown that references to the memory at any given interval of time tends to be confined with a few localized area, and this is locality of reference. Now that is, if we use a function call or a loop in our program, then in our program more than once our program flow will move on location of loop or function body again and again. So what we can do is we can keep this kind of active partition in a fast small memory. Then the average access time can be reduced. Now instead of accessing the same from the RAM, we can access it through the cache. So the fast and small kind of memory can also be referred as a cache memory, in which an active partition which is accessed again and again can be kept. Now here in diagram you can see the cache is placed between main memory and CPU. In memory organization part 2 video, I have discussed what is L1 cache, L2 cache and L3 cache. Please go through that explanation also. The only reason we are trying to keep frequently accessed block in cache is its access time is less than access time of main memory. The data kept in cache can also be called as words. Now when CPU wants a data or a word, it is first checked in cache. That is, when CPU wants some data or wants to request a data, it checks for the same data in cache. If it is found, then it is accessed from the cache, and if the required data is not found in cache, then it is being searched in main memory. If the content is available in main memory, then what happens? It is accessed from the main memory. After this, the same data is transferred to cache for the future reference. So CPU doesn't have to search in the main memory, and the same data can be accessed from the cache memory and time can be saved. Now let us have a look at the animation of what I just explained now. Now here we have a block of CPU and we also have two different blocks of cache and main memory. Now initially whatever CPU is requesting, it is being searched first in cache. If the cache doesn't have the searched data, the search goes to the main memory, and the same thing is searched in main memory. If the same data is available in main memory, then what happens? Let's look at the same in a different animation. as data was not available in cache and it was available in main memory. Now the main memory is sending or storing the data in the cache for the future reference. Let us understand how cache performance is measured. Now, whenever the data is required, whenever the data is requested, data or word, if it is available in cache, it is known as hit, and the performance of the cache is measured in hit ratio. If the word or data is not found in cache, then it is known as miss. Hit ratio can be found by number of hits divided by total number of reference. The result can be the performance of cache. Now we know that whenever the data is not found in cache, it has to be transferred from main memory to cache. This transformation of data from main memory to cache is known as memory mapping. We have three different kinds of memory mapping. First is associative mapping, second is direct mapping, and third is set-associative mapping. Now let us see what is associative mapping. We have previously discussed what is associative memory or CAM, and in this mapping the same concept is being used. Associative type of mapping, which memory it stores both address and data, that is content. This memory can store any data from main memory. Now if you remember, we had one argument register in CAM. The same argument register is being used here also in order to search or refer something. Whenever CPU want to refer or search a particular data, it generates 15-bit long address to refer, and it places the same in argument register. After this, the content of argument register is matched with the matching address. If found, the corresponding data is read and sent to the CPU. Now let us look at the diagram. Now in the diagram we can see CPU has kept 15-bit block to refer, and it can be placed in address argument register. The same is being searched in associative cache memory, and if found, it will be returned to the CPU. You can see in the diagram we have two pairs. The two pairs are available in the memory. One is of address and other is of data. The left hand side address is in octal format, and right hand side data, now that is 12-bit data which is available in the cache, which CPU is requesting for. Now if CPU requested data is not available or doesn't match with the cache content, the main memory is accessed. Now when the main memory is accessed, the address and data pair has to be transferred to cache also, so in order to use it for the future reference. But what if the cache is full? Now if the cache is full, the same pair, the pair of address and data, must be placed somewhere. Now in order to place this, we have to remove a particular data from the cache which is not needed. Now this decision of removing an old pair is determined by replacement algorithm, and the replacement algorithm can be selected by system designer. The system designer will choose which type of algorithm to use. Now in this we can also use FIFO replacement in round robin manner, that is one after another, first in first out. Now let us see what is direct mapping. Now associative memories are expensive compared to random access memories because of added logic. So we are trying to go to a different approach of a memory mapping, that is also known as direct mapping. Now the CPU address, the CPU whenever it refers something, it is referred in 15 bits. So these 15 bits are divided into two parts. The first part is known as tag and other part is known as index. The tag is of 6 bits and the index is of 9 bits. The index field is equal to the number of address bits required to access cache memory. That means if you want to access something from the cache, this index will be used, which is of 9 bits. As we can see in the diagram, the CPU which is trying to refer something, the address of 15 bit is divided in tag and index. Now below that we have shown here in the diagram that we have main memory which is capable of 32k into 12 words, and we have cache memory which is able to address 512 into 12 words. Now see the address. Main memory is able to address 15 bits while the cache memory is able to address 9 bits. Now if you compare main memory and cache memory, one thing is common, that is data. The data bits are of same size. If I want to access something from the cache, I can use it from the index address. Index address of main memory and the cache memory are of different size. As you can see here, address is of 15 bits and in the cache memory address is of 9 bits. The 15 bits of address which is used in main memory is divided into two portions, tag and index. Now here in the diagram, it is the internal organization of main memory and cache memory. Now you can see that in main memory the addresses of data is of 15 bit. That 15 bit address is divided into two portions. First portion is tag, second portion is index. Now the index of main memory and index of cache is 000. Now tag here is 00. Now you can see here. Now I'll explain it by zooming the diagram and comparing it with the content of main memory and cache. The tag part here is 00 and index part here is 000. Now if you compare it with the cache memory, we have index part outside the cache which is used for addressing the content, and tag part is inside the cache which is used to access the content. Now if you compare main memory and cache memory, the content of both the memory in first place are same. Now let us take an example of another. Now 777. Here if you compare the sixth line in the main memory address, 777 can be the index address and 02 can be tag. Now compare both the content, main memory and cache memory. You will find the same data, that is 6710. Now as seen in the example, each word in cache consists of data word and its associated tag. When a new word is first brought into the cache, the tag bits are stored alongside with the data bits. That means whenever the cache is filled with the data, the tags related to that particular data is also stored in the cache. When the CPU generates a memory request, that means whenever the CPU wants to refer anything, wants to access something, then the index field is used for address to access the cache. That means at that time, whenever the cache is being searched for the data, index field will be searched. The tag of CPU address is compared. Now we already know that 15-bit is divided into tag and index. Now the tag will be searched for the particular data. If that tag and the CPU referred tag is a match, then this is known as hit and data will be found. But it can be a case where there is a miss, that means a data doesn't match. So at that time the required word is read from the main memory, that is nothing but a RAM. It is then stored in cache together with new tag replacing the previous value. But one of the major disadvantage of this direct mapping is the hit ratio can drop considerably if two or more words whose addresses have same index but different tags are accessed repeatedly. That means it can happen that the address part matches but the tags are different. So in this condition, what we have to do is we have to replace that block with a new block. So data will not be found in cache, so main memory will be referred, and from that we have to write the data onto the cache. We have to replace the block in the cache. The third type of mapping is set-associative mapping. This mapping means we'll have a set of block and data together. Now after looking the diagram you will come to know what it is. It is an improvement over the direct mapping. The direct mapping, I told you, the disadvantage was we have to replace the block if the tag doesn't match. Now in this type of set associative mapping will not be needing replacement of the block. Instead of that, we can save it in the pairs, as it is mentioned on the side that direct improvement over the direct mapping organization, in that each word of cache can store two or more words of memory under the same index address. That means on a same index address you can store two or more data with a different tag. Now you can see in the diagram as well that the address is 000 but the tag is 01 and 02. So the complete address can be 010000, second address will be 02000. So both the address with different tags are stored on the same location index, that is 000. But this mapping will have to address more amount of data, that is it has to address 36 bits instead of 12 bits, because each tag requires 6 bit and each data word has 12 bits. Data size is 12 bits. So the word length is 2 into 6 plus 12. Tag is of 6 bit, data is of 12 bit. 6 plus 2, 18 into 2, that is 36 bits. Now same as paging, we also have replacement algorithm in mapping, because whenever a particular block is not found in the cache, then we have to bring that block from main memory to the cache memory. So if the cache memory doesn't have a particular block free, we have to remove some block to allocate a new block. So there are some replacement algorithm that can be used during replacement of the block, and they are first in first out, least recently used. I hope you all will be familiar with how the first in first out and least recently used method works. Let's move on to next slide. Now we also have one subtopic related to it, that when we are writing into cache, that means when you are writing something into cache, how it should be or in which manner it should be. We have already seen how the mapping works and what are the different types of mapping. But when you are writing into the cache, it can be done in two ways, that is write through and write back. Write through means you are writing your main memory as well as cache memory all together. That means we are writing cache and memory parallelly. So that means the block whichever is stored in cache and in main memory will be same. But when I talk about write back, that means if a particular block is brought onto the cache for writing, then the same block is written onto the cache, but it is not updated at the same time on the main memory. What we have to do is, whenever we are trying to remove this block from the cache, at that time we can write it onto the main memory. The updated copy will be written. Discussing it again, two options to write into cache: write through and write back. Write through means writing main memory as well as cache memory together. For an example, if I want to access particular data, so I am making modification in both the location, in the cache as well as in the RAM. But when I talk about the write back, that means when I am bringing one block onto the cache and I am modifying this copy. So what I'll do later, that I'll not modify the same copy of the block into the main memory, but I will keep on modifying the block which is lying in the cache. After this block has to be removed, at the time of removing this block, we can modify it onto the main memory, and then it will be stored onto the hard disk. So what we are trying to do is updating the data, nothing else. The best example to understand this is opening a file and modifying it. When you are opening a file and when you modify it, if you don't save the content, the same file will be saved. But when you save the content, a modified file will be saved. This is nothing but an example to understand the write back. The last topic of this chapter is virtual memory, and we'll be discussing this in a next part of the video. Thank you.